Shall we start?
Yes, please.
Go ahead.
Okay. Good afternoon, everybody. Thank you very much for the introduction that Dr. Suleiman and Dr. Aminzadeh gave us. And this is Alireza Mollaei. I'm the reserve engineer side of this presentation. I'm going to start this presentation and for the first section, and then it will be continued by Dr. Alireza Shahin, more on the geophysics part. So the topic we chose for you, I'm going to share with you in the next few slides, is focused on the intelligence carbon storage, coupled with the benefits of the EOR and also for the monitoring. In the next few slides, we're going to start with the motivation of this work, and then continue with the enhanced oil recovery, coupled with carbon storage. I'm going to share with you the different aspects of the CCS coupled with EOR, screening part, technical backgrounds, and then different types of models, including artificial intelligence models. And I'm going to end this with some field case studies. And then in the next part, Dr. Shahin is going to continue with the geophysical techniques, including the seismic characterization, microseismic, electromagnetic, electroresistivity, microgravity, multiphysics, and then end up with a summary. The motivation of this work started with how we can kind of leverage the high expenses of the CO2 capture and sequestration with getting benefits of some utilization process. By utilization process, I mean the process that we use the CO2 stored in the background to get some money out of it, something like EOR. So we know that the enhanced oil recovery using CO2 has been around for many decades. It has been widely used, especially in Permian Basin reservoirs. So the fact is that so when we have the skills and the experience of using CO2 for enhanced oil recovery, why shouldn't we use it as a leveraging techniques to kind of actually have this CCS process more economical? So actually, for this, a very true and complete screening is going to be necessary to choose the right reservoir to give us not only a good enhanced recovery performance, but also a good trapping capabilities. So we know that, as a matter of fact, after many years of working in different companies, that a big portion of the company's assets, especially in the US, are depleted reservoirs. They need to go under tertiary recovery, and many of them are good candidates for CO2 flooding because of very good and very compatible properties of the CO2 with the reservoir fluids. So the chances of the CCS, as I already told you, is that it is going to be actually increased by combining with CO2, especially when we have a very nice and very helpful geological trapping on the ground, including structural or stratigraphic trappings, residual ozone, solubility, mineral. These are different trapping techniques for CCS techniques. And actually, for this work to be successful, we do need integrated reservoir studies, including multidisciplinary G&G engineering data analytics program to be working together as a team, a very tight team, to have this, to get a good results out of this. So we can actually monitor the real-time CO2 injection and trapping by getting use of the different techniques, including the analytical and also machine learning techniques. And also, we should always consider the health and safety and environmental issues, to compromise and meet the standards of the federal government and the local government. This is our high priority as well. So to give you some just technical references, we work on the CO2 flooding WAG for different companies, especially Chevron, and we came up with the new models, analytical models, and also we did lots of numerical simulation. These are the references if you wish to take a look, and also some internal documents that with BP actually we worked on the data science and machine learning techniques. Some of these are US patents, but I'm sure actually you can find similar references in the papers I mentioned. So this is just one of the outputs of the analytical modeling that we did for one of the famous Permian Basin CO2 projects, Sakurat project. I'm sure most of the people here probably know that. So we came up with some novel analytical models to very fast match the history and also give us reliable prediction for the performance of the CO2. I say performance, I mean key reservoir engineering variables, including oil rate, cumulative oil recovery, oil cut, saturation, and same could be used for the CO2. The importance of these models is that we can use these analytical models instead of numerical model to train our neural networks, artificial neural networks. So because you know that a numerical simulation is time consuming, could have many challenges, but using analytical models instead, when you don't have the time or the money budget for running lots of numerical simulation to train your network, you can use this analytical models instead. Well, this is a type of work that we did on some other topics at BP. These are only, the documents are kind of confidential, but I'm going to show you just some brief just to give you some ideas. Okay, how we use some internal softwares to build the neural networks and train it, and then use it for history match and then prediction for well scale and also field scales. And most of the times these kind of techniques are used when the numerical simulation is not able, because it's not able to give us a reliable history match or prediction because of the complicated physics, including like unconventional reservoirs or some other cases. So these type of projects are very good candidates for using the artificial neural networks and data science techniques. Well, in the next few slides, I'm going to share with you some field cases that they use the artificial neural network to match the history and also produce a reliable prediction for both for the cumulative recovery and also CO2 storage in a CCS projects coupled with EOR. So this is one of them done on the one of the Pennsylvania reservoirs. And as you see on the left, the graph on the left gives us the match and also the prediction for the cumulative recovery. And the chart on your right side give us the same thing for the CO2 storage and how much CO2 we were able to store underground in the reservoir during the CO2 EOR process. So the terms I'm showing in this slide are the CPS stands for the purchased CO2 or the CO2 that we captured and inject into the reservoir. C Pro is produced CO2, which is the outcome of the EOR process, and CR is the recycled CO2. So the retained CO2 or the CO2 storage is going to be the CP plus CR minus C pro. So as you see, in this case, the authors actually they did try to optimize this case compared with the base case, and they were able to use the neural network after validating the network to optimize the project. The next case was done on the I guess 4 or 5 of the Permian Basin reservoir, including the famous Wassenfield, Robertson, and a couple more, I guess. So again, they try to build up a numerical simulator to train their network using a CMGGM. They used more than 350 samples to well train their neural network. And after making sure that the neural network is working well, as you see on this slide, with the R squared close to 1, they use this network for optimization and prediction. So I should mention that okay, they use 7 uncertain parameters to build up their training samples, including the reservoir thickness, porosity, permeability, residual saturation to water flood, residual saturation to gas, which here is CO2, bottom hole pressure, and CO2 injection rate. Well, then this slide actually shows the economical evaluation of the CCS process coupled with EOR. They use the typical values for the oil price, including the variations during time, and CO2 capture, separation, compression, and different kind of actually expenses that they had. And they try to optimize NPV, which is the heart of a successful project, to make sure that the project is going to be economical, the project of the CCS combined with EOR. So as you see on the graph, that they were able to use the neural network to optimize and actually increase their NPV over time, which is a good actually news for us, that they did it. They used it for I guess 4 or 5 of the Permian Basin reservoirs, and they showed that okay, this is going to be economical, even in this fairly low oil prices. Nowadays we're about like $80, so I think it's going to be more economical if you do it. So with this being said, the first part of this presentation is done. I'm going to actually leave this to my colleague, Dr. Alireza Shahin, and he's going to continue from here. Thank you very much for your attention.
Okay, can I have the...
Good. So Alireza Shahin, maybe you can take over and discuss your focus area.
Yeah, I'm just thinking, should I share my presentation myself, or can I get the control? I think it's probably better to share myself.
You don't need just, you can just use the same, unless you want to control movement of these slides, you can just do it either way.
I just stopped sharing.
Great, thank you, man. Share. Can you see my screen now?
Yes, we can.
Yes.
Right. Good afternoon, everybody. Thank you so much for your time. I'm going to quickly actually pass this slide that I already presented and go to my own slide. Yes, as Dr. Mollaei mentioned, we're talking about the underground capture, underground carbon storage here. And of course, one of the important tools that we need to monitor the storage is geophysics. And here I'm showing a few geophysical methodology, basically to summarize what I'm talking about. So as you know, by injecting CO2 into the either reservoir or reservoir to do the enhanced oil recovery, or to inject CO2 into the saline aquifer, we expect some changes in the reservoir properties, rock properties and fluid properties are going to change. And of course, we have more complicated kind of story to tell after injection. So let's just assume that we are injecting CO2 into a saline aquifer. So we're expecting to have some decrease in the density. So if you can see my cursor in the gravity section here, by increasing the density, we expect the gravity measurements are going to be changed because of the change in the density. And then at the same time, we are expecting to see some changes in electrical resistivity of the rocks, because CO2 is going to replace the brine, and then we expect some increase in electrical resistivity. And at the same time, due to the injection, we expect some level of the decrease in seismic velocities, including P wave velocity and S wave velocity. So all these changes can be captured by different geophysical techniques. Velocity changes are going to capture by seismic. Is going to be captured by gravity measurement, and changes in the electrical resistivity is going to be captured by electromagnetic or electrical method. So the aim is to kind of do forward modeling and inverse modeling and get the saturation of the CO2 changes in the pressure. And we also might want to estimate the porosity of the reservoir and the degree of the patchiness for the reservoir for the CO2. So this is kind of the big picture of the following slide. As an example, and one of the actually good examples of the CO2 injection in North Sea, we have the reservoir top here, sitting here, and then reservoir bottom right here. And this is the first survey acquired in 1994, and then they have a monitor survey back in 1999, and then the following monitor survey back in 2001. And you see the injection of the CO2, we see all this nice bright spot here, both in the cross section as well as in the map feed. So this is one of the nice examples. We see the changes in the seismic amplitude in the previous slide, and this slide you see changes in the time shift. Assume this is the reservoir bottom, reservoir base here. And the blue line here shows the base before the water injection, and the green curve here shows the base of the reservoir in the time domain after the CO2 injection. And this is because of the velocity push down that we are expecting, because we are injecting CO2, we're expecting the decrease in the seismic velocity, and by decreasing the seismic velocity, we're expecting the increase in the time between two seismic surveys. So all these things, are going to help us, this kind of the measurement, this kind of the data, either in the seismic amplitude, also in the time shift between two different seismic surveys, are going to help us to monitor the CO2 injection in terms of the font, in terms of the quantity, the volume, and lots of other parameters that we are interested to know when we injecting CO2, either for just storage, or when it is coupled with the EOR, and also seismic itself. Either just the 3D seismic itself is going to help us a lot. Although I'm not going to talk about the 3D seismic characterization here. This presentation is more focused on 4D monitoring. So the seismic itself, the 3D seismic itself, is kind of one of the vital component of any UCS project, because basically we want to know the structure of the field. We want to know all the details about the fields, and then all the faults, fractures, and everything are going to be characterized by seismic 3D seismic surveys. And then we are going to start the monitoring using different seismic data set that we are going to acquire the years actually after the first base survey. So here I'm showing the integration of the gravity surveys and seismic data. This is a very recent paper. They started with the prior realization of the geological model, including the porosity and permeability, and they ran the fluid flow simulators, and then getting the values of the CO2 saturations at different time steps. And using these saturations, porosity, they can start doing the forward modeling for gravity data as well as for the seismic data. So they model the acoustic impedance data and also they model the gravity data in the top part. And then using the inversion scheme, they obtain the saturation. So this is very kind of similar to the history matching that reservoir engineers used to do, but here we have more data to match. We need to worry about matching the production, matching the injection. I mean, probably here we don't have production, but for the injection of the CO2, we need to match the history of the injection. And we also need to match the seismic data as well as the gravity data, because we have several suite of the seismic data and the gravity data, and these gonna be added to the history matching group. And this data is gonna help us to monitor the monitor the CO2 injection and come up with a better estimate of the CO2 saturation. This is another recent papers, which I call it machine learning monitoring. They start again with a set of known cases, including the known total dissolved solid, they call it TDS, and then known pro pressure cases and known CO2 partial saturation. And so these things, which all the output of the reservoir simulator is going to be converted to the seismic velocity model using the known or assumed rock physics model. And then we again do the forward modeling, for example, using finite difference modeling, or maybe a little less complex seismic modeling algorithm like reflectivity or even convolutional model. And we're gonna gather the synthetic shots and using the engineering feature extraction, we can start extracting several features, several attributes, like amplitude kind of related attribute, phase kind of related attribute, and any other kind of attribute, either as a signal or as an image. So if you start extracting the features, we can also do deep learning, or we can choose to do machine learning if you want to just work with the time series data. So after the extraction of these features, we can start training a model, a machine learning model, or a deep learning model. And basically we have several known cases here, which are the discretizing CO2 saturation. So we can label this as a known classes, and then we can end up predicting CO2 saturation on the unseen data. So as you see, this is kind of integration part of the story. Reservoir engineering is a big part of the program. Geophysics is also a big part of the program. All the new advanced machine learning, deep learning algorithms are a big component of this program. So just back to see the main changes happening in the seismic domain in the terms of the seismic velocities. I have one slide here just to quickly show how increasing the CO2 saturation from left to right. If you just see the top chart here, you see the CO2 saturation is started from 0 and go all the way to 100%. And then we have normalized seismic velocity on the vertical axis. And basically that blue line or blue curve here in the middle showing the saline aquifer. And by increasing, the water saturation, the CO2 injection, we are going to have a big change, in the seismic velocities. It started from 1 here when we have 0% of the. By 100%, you see there is a big decrease in the seismic velocity from left to right. And, and this is not unique. And the main culprit is here, how is the distribution of the CO2? Depending on the CO2 distribution that could be uniform, we can do the modeling using well-known Gassman equation in red. And then if we have more kind of patchy CO2 saturation behavior, we can, use, the patchy line, which is the black line here. So you see, this is not a unique case, and geophysicists has been actually ignored this kind of a behavior for a long time, especially when dealing with the not very complicated monitoring study. But for CO2 is very critical, to take this to account this kind of the complexity, especially the patchiness behavior. So these days, actually, geophysicists, take into account this patchiness behavior as the model parameters to be estimated through the inversion, either physics-based inversion or data-driven kind of the estimation, or a hybrid case, which is a combination of the physics and data-driven technologies. I don't know if I'm behind. We still have time. Is that right, Alireza?
Go ahead if you have a few more minutes.
Okay. So I have a couple of more examples here about the seismic and how we can estimate the porosity from seismic, how we can estimate the porosity and shale content of the seismic. I'm going to pass them quickly and go to microseismic and some other geophysical measurements. I'm going to quickly touch on those and then go to the summary. So as you know, in terms of the hydrofracturing, the microseismic or microearthquake, we call it MAKE, has been used in industry for a long time, and we can use the same technique for the underground gas storage and underground carbon storage. And this technique is going to help us a lot in to identify the focal point. We can basically do advanced seismic data processing and imaging to accurately locate the events and image the focal mechanism of these events, and that's going to help us to identify the fracture distribution and also the focal point, and it's going to also help us to identify the leaky part of the fault or the leaking faults, which are very important for the underground carbon storage. So with that said, I have a couple of slides talking about the electromagnetic, but because I know Professor Kurt Strack, a well-known electromagnetic expert, is gonna have a separate talk on the electromagnetic. I'm gonna pass this slide, and I think in July next year, I believe we are gonna have a great presentation on this subject about the 4D monitoring. I have some stuff here. I would be happy to share, and talk about that offline if you want, or after the presentation. But because of the time, I'm going to skip this part for now. Just going to the last part regarding the microgravity. Recently, this microgravity with the advance in the instrument has gained more attention. As The main issue that we have with microgravity is the accuracy that we need to monitor the CO2 plugin or any kind of the changes in reservoir properties that has to be monitored. We need a very accurate measurement and instrument to do so using the microgravity. Here, what I'm showing is a recent paper showing that if you have that
We can't hear you. Can everyone hear me? Hello? Can everyone hear me?